Hello. Hey, how about we wrap up Unit 1? That's right. We're in our last key concepts, Unit 1, Part 4. This is the topic. This covers the topic of alcohol. So Unit 1 had benzene. That was a major component. But we also squeeze in the OH group, the alcohol functional group, into Unit 1 too. A lot of this is going to be review because we saw alcohols last semester. We just formally haven't talked specifically about the functional group. So let's fill in a few gaps. Okay, so Unit 1 Part 4 of our key concepts begins by talking about acids and bases again. You can never get away from those. So it turns out an alcohol, like water, behaves like a weak acid and a weak base, right? Water can donate H+, alcohols can also donate H+. Water can accept an H+ and be a base, and alcohols can also accept H+ and act as a weak base. That actually is a little bit of review from last semester when we were talking about E1 and E2 reactions. So you might want to go back and review that. Or stick around because there's an opportunity to review E1 and E2 reactions in this video too. Okay, more importantly though, I decided to just put together a compact little video just talking about acids and bases, specifically how to determine whether, if you're given two molecules, you're trying to decide which one is a stronger acid or which one's a stronger base. So take a look at that video. It's very helpful. And it's a topic we'll keep coming back to. Acids and bases, like I said, you can't get away from. So it's nice to have that one video, the review acids and bases, whenever you need it. Continue on with the alcohols though. First thing we typically do is name them. So it's pretty straightforward. For common names, this is review. We talked about this last semester. You just use the format alkyl alcohol. So if you have CH3OH and you want to assign it the common name, this is the methyl group, and this is the alcohol functional group, and you put them together with a little space in between, and you got the name, methyl alcohol. Yep, so the alcohol found in beer and wine is ethyl alcohol, 2 carbons. Methyl alcohol can give you a buzz, but it also causes blindness. So no thank you. Rubbing alcohol is a common name. Another common name is also isopropyl alcohol. Okay, and let's see, there's 2 more. I mean, that's a very common name, right? You've seen isopropyl. It's actually an accepted IUPAC prefix. 3 carbons, but attachment in the middle carbon is isopropyl. So you have to know that. And then here's 2 more that you need to be familiar with. Again, review. We talked about the group with 7 carbons, where there's 1 carbon attached to the benzene ring. That's the benzyl group. And so the common name for this molecule is benzoyl alcohol. Cool. 3 carbons with a double bond and connection to a new group at the carbon that's not double bonded. That's an allyl group. There's 3 L's to remind me there's 3 carbons in this group. And then these lines kind of look like a double bond. So yay, there's a double bond right there. And the carbon that doesn't have a double bond is like, poor carbon, no double bond for you. Well, no, that one gets to hold on to the extra group, in this case, an alcohol. So this molecule is allyl alcohol. Nice. Some of you might be saying, wait, what about vinyl? Well, you can draw it. Vinyl is 2 carbons double bond together, and then you attach an alcohol here, but it turns out it's in equilibrium with the aldehyde. We'll see that in Unit 2. So technically there is no vinyl alcohol because it rearranges, isomerizes to acetaldehyde. I think that's how you say it. 2 carbons with an aldehyde. Common name is pretty straightforward. If on the exam I ask you to name something, and you readily see, ooh, I know the common name. You can give that name for full credit. More commonly, though, the molecules will be somewhat complicated. A common name won't be useful. You have to actually switch to the IUPAC naming system. So let's review that real quick. There is a handout on Canvas in this assignment folder. So at the end, should be some resources, one of which talks about nomenclature. I think it's called naming organic compounds. First page looks like this. Breaks down the structure of the IUPAC names, and then you scroll down maybe the third page, you actually have the steps. And I just want to review this part right here because it's going to come up today. Step 1 is identify the longest chain or ring that contains the highest priority functional group. So unfortunately, the way we teach organic chemistry, we have students name alkanes first because it's the simplest. The problem, though, is students get really good at finding the longest chain and declaring that to be the parent. Well, the rule changes a little bit once you start adding more functional groups. The longest chain is not automatically the parent. No. IUPAC wants to put the highest priority group on the parent. So do that first. Find your highest priority group. Sometimes I tell students that's step 0. Find highest priority group, high priority functional group. Go find it. That carbon to which that priority group is attached is part of the parent. And then to that carbon, see which is the longest chain or ring that you can discover. It may not be the greatest number of carbons in a chain. So I'll try and clarify that in a second or two. Okay, let's see some examples. Oh, before we do that, a little more info. How do you name molecules that possess an alcohol group? Well, if the alcohol group, the OH group, is the highest priority functional group, you denote it with a suffix. And the parent name with OL, because that's how the word alcohol is ending, OL. So the suffix for the alcohol group is OL, OL. Yeah. If the alcohol group got beat out by a more important functional group, then you identify the alcohol group with the prefix hydroxy, which is kind of nice because OH minus is hydroxide. So a good connection there. So cool. All right, so how does that play out? Well, here's an example of this second rule. We haven't talked formally about how to name carboxylic acids, but we do know how to name this one. Right? So a carboxylic acid attached to benzene is benzoic acid. Oh yeah, and some of you are saying, wait, but we have another parent name that's possible. What about this one? Phenol, phenol, whatever. PHENOL, which is the true parent name. It's the one with the higher ranked priority group, higher ranked functional group. Well, how do you know that? The pattern is more pi bonds, more oxygens make it more important. So between an alcohol group and the carboxylic acid group, carboxylic acid clearly wins. It has a pi bond that the alcohol doesn't. And in a carboxylic acid, there's 2 oxygens, not one like the alcohol. So this is your parent. This one loses. The more important functional group determine the parent chain. And with benzene derivatives, fancy name for molecules possessing benzene, wherever that new group is, the most important functional group is, that decides carbon number 1 of the ring. So the alcohol is now on carbon 2, and you can't use the ol suffix because we already have the oic acid suffix for the carboxylic acid. You must use hydroxy. So you can choose 2-hydroxy, or you can use ortho hydroxy, benzoic acid. Either name will give you full credit on the exam. You don't have to give me both. Nice. Okay. New problem. Let's name this. Step 0. Find the highest priority functional group. Is that the alcohol group, the alkane? No, not the alkane. Or the benzene ring? Well, pattern is, the trend is more oxygen, more pi bond, more important. IUPAC decided to break the tie with oxygen. So the alcohol functional group is the most important one. If you're more concerned about ranking functional groups, take a look at the handout again on Canvas called Naming Organic Compounds. So here it is. And if you scroll to the second page, there is a listing of functional groups by their priority rankings. Carboxylic acids are at the top, followed by acid anhydrides. If you look down the list, here's ketones and aldehydes. And then there's the alcohol group. I see it there. Hey, where's benzene? It's not even on here. It's kind of lame. Lame chart, I should say. The alkenes and the benzene kind of are tied here. There's phenol. Ooh, that's helpful. Phenol, benzene ring, and an alcohol got outranked by the silly alcohol group. IUPAC, what are you thinking here? Anyways, oxygen is more important with ranking than pi bonds. Oh, okay, so that list, I don't advocate memorizing it, just get used to the pattern. Back to our example. Step 0 then says, with this molecule, the alcohol group is more important, meaning that carbon, give me the pen, there it is, that carbon is part of the parent. So find the longest chain or ring, not both, find the longest chain or ring containing the most important functional group. Well, the alcohol is the most important functional group. This carbon is here, so my longest chain is right here. Do I include this carbon? Nope, that's a ring carbon. So ring carbons are not chain carbons. It's a chain of 4. That's my longest chain with the most important functional group, and it outbeats a ring of 6. IUPAC. Now, I guess we just have to get used to it. Step 0, and maybe add that in. Find your most important functional group. That found the first carbon or a carbon of the parent. Doesn't have to be the first one in this molecule. Let's see. So I think I did step 0 with the alcohol, most important group. Step 2, find the longest chain with that functional group. Did it. Step 3 is to name the parent. It's a chain of 4. So it's butane. Before I think about stopping, ending the name, butane, pull off the E and add an OL. So I got the right suffix. That's step 2, parent name with the proper suffix. Step 3, number that chain. Okay, so are we numbering from this end, the left side, or the right end? Well, you do so to get to the most important functional group as fast as you can. Whoever gets a suffix gets a priority on numbering. All right, so the alcohol group's on 2. Well, what's this extra group on 4? Well, that's benzene, but the word benzene is a parent name. I have to use a prefix name, phenyl. And it's on carbon 4. So the full name is phenyl, and then we have to identify where the alcohol sits. It's on carbon 2, butanol. Or you can put the number 2 right next to the, sorry, that's not right, right next to the suffix. And that's actually IUPAC's latest recommendation. However, they still say the first one is still valid, and I'll accept that. And I will too. Give me either one of these names on the exam for full credit for that molecule, if it shows up. Okay, more nuances of the naming rules. Okay, step 0, find the most important functional group. 3 halides, don't they beat up 2 oxygens? No, they don't. The alcohol group's the most important. There's 2 of them. They're also on the parent chain. Well, that's pretty clear. There's only a chain of 5 here. Cool. Chain of 5 is pentane. And before I think about tacking on E, I think about adding OL, but is that going to be the right full suffix? Let's kind of preview ahead. When we're going to get ready to name these chlorines, do we say this is, chloro, chloro, chloro? No, we say it's trichloro. We only say the word chloro once in the name, and we put a new prefix, di, tri, tetra, penta, whatever, to indicate how many times that group shows up. Same pattern here. We have two alcohols. That's a di, right? Two chlorines would be dichloro. Two alcohols will be a diol. You just tack it onto the suffix. And then IUPAC says, well, wait, your new suffix starts with a consonant, so you can keep the E this time. So if you're worried about spelling, pentane diol, you keep the E. And other ones where the O goes right up against, would go against the silent E, you have two vowels connecting, that's when IUPAC wants you to drop it. Now in my class, I don't take points off for that. That's just a minor spelling error and I ignore it. I'm giving points for pentane. And if you have the E or not, I don't care. You gotta have the di in there as well as the ol. Get all the points. Oh wait, we need more points. We have no numbers here. That was step 2. We named the parent, pentane diol. Okay, now we have to number the chain, getting to the most important function group as fast as you can. Well, then number 1's over here on the right again. And then you walk down the chain and name all the groups. The alcohol is showing up on carbons 1 and 2. And then the 3 chlorines are on carbon 5. So will this fit? Probably not. I'll make it though. Trichloro -1,2 pentane diol, or 5,5,5 trichloro, right? If you have 3 chlorines, you need 3 numbers. You have to be very specific. If it's left off, then where are the chlorines? It could be on any of those 5 carbons. Pentane, and then you can insert the 1,2 here if you like. Diol. Your choice. They both earn full credit. Another one here. Okay, what do we got? We got an alcohol and alkene. What's step 0? What's the most important functional group? It's the alcohol. So this is part of the parent. Chain of 5. Okay, this one's a little trickier because when we name the parent, we definitely have to add the ol suffix because that's the highest priority group. But alkenes and alkynes, double and triple bonds, don't have prefixes. You have to use a suffix. That's annoying. That's the way IUPAC set it up. So the parent name is going to be pentane, but you switch it to pentene because of the alkene. You drop the E and add the ol. Pentenol. Fun. Where's carbon 1? Most important function group, they decided that right here at the beginning of the chain, the alcohol sits there. So there's carbon 1. Okay, so the alcohol starts on 1. I think about putting it here, beginning. The double bond began on 4. I think about putting it out here. Okay, if you put 1,4, I'll do it, but please don't do it. Put in parentheses because this is incorrect. It is unclear whether the alcohol or the alkene begins on 1. We don't know, can't tell. So you can't do it this way. You must at least have one of those numbers next to suffix, and I would just advocate putting them both next to them. So we got a chain of 5 is pent. The double bond began on carbon 4. If you leave the E in there, I still give you full credit, but technically we're still supposed to drop it. So you can put in the 1, then the ol suffix. Oh, little red flag. Hopefully you're thinking that from last semester. Anytime you're naming an alkene, check for cistrans or EZ. You have to put that in front of the name too if it's possible to have an isomer. We don't here, right? And the best, I don't know about the best. The way I check is go to one alkene carbon, find its 2 groups, and then switch them. Well, switch an H with an H, there's no change in the structure. But if you change its 2 groups on one alkene carbon and it makes a new molecule, then you do have an isomer, and you must use either cistrans or EZ, depending on what works. E and Z always work as long as there's EZ isomers. So I would push towards using E and Z, but sometimes cistrans is easier. IUPAC, lots of choices. Yeah, last one, hairy one. Step 0, find the most important functional group. That's the alcohol. Okay, that's a little annoying because I'm looking at this long chain horizontally here thinking, isn't that the parent? Nope. This carbon is part of the parent because it's attached to the most important functional group. Okay, then we know that this part must be the parent. And then now how do we go down the fork in the road? We'll start heading to the left where there's more carbons, because the rule is find the longest chain or ring with the most important functional groups, plural. What about this alkene? Okay, how are we going to name that alkene? Well, there are some loopholes. You could try naming it with the vinyl prefix or the allyl prefix. How do they work? Vinyl, you just saw it, is when you have, well, I shouldn't put an alcohol, let's make it an ether. Vinyl is when you have 2 carbons double bond together attached to something else. Allyl is when you have 2 carbons double bond together and a third one attached to something else. That's the allyl group. So here's going to be, maybe you want to call this the parent and you're thinking about, well, can I use allyl or vinyl on this thing? No, you can't. The parent, if you want to call this the parent, is connecting at the double bond. That's not allyl. Darn it. So you can't do that. Get rid of my dotted lines. Okay, so if you can't use these two and you can't use phenyl, well, that's not an alkyl group. Why don't we even bring that up? Alkene, I should say. Yeah, these are the only 2 we got so far in organic chemistry, at least when I teach it. Those are only 2 prefixes. You must use a suffix. You have to use the -ene suffix, which means to use a suffix, it must be on the parent chain. So here is our parent with the most important functional groups, plural. I know that's not very satisfying because there's clearly more carbons here, but that's IUPAC for you. It also makes for an easier name. Since we can't use these prefixes here, it would be a very complicated name if you tried to use this long chain. So don't do it. Make it a little easier on yourself. Here's the parent. IUPAC accepted. Okay, found it. That was step 1. Found the longest chain with the most important functional groups. Step 2 is to name it. All right, so I got 1, 2, 3, 4, 5, 6, 7, 8 carbons. That's octane. Change it to ene. And then think about the E, and I say, nope, we're going to add the ol suffix. So the parent name is octenol. Step 3 is to number it. Well, don't start numbering from this end because the most important functional group is the alcohol. So you have to number from this side. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now walk down the chain and name all your groups. Well, carbon 1 doesn't have anything. Number 2, I see something poking out of my bubble. I bubbled my parent chain. That's alcohol group. So on carbon 2, there's the alcohol. 3, 4, ooh, something else popping the bubble. A chain of 4 carbons. Molly eats peanut butter. Butter reminds me of butyl, butane, which then is butyl. Yeah, so on carbon 4 is the butyl branch. 5 has a 1, 2, 3, 4, 5, 6, 7, right? You're not counting the parent carbon. Don't count number 5. There's 1, 2, 3, 4, 5, 6, 7 carbons. 7. Let's see. The heptathlon is the Olympic event for the women where they participate in 7 events. And that's the 7 carbon group is heptathlon. No, it's heptyl on carbon 5. Heptyl, heptane, whatever. That's a Y. Carbon 6 begins the double bond. Ooh, red flag. Is there a Cistrans Isomer or EZ? The answer is yes. You can kind of see it's kind of zigzag crooked. There's a hydrogen here and a hydrogen there. The identical groups are on opposite sides of the double bond. That's a trans isomer. If you don't want to use trans, then you'd say, okay, on this, let's change colors. Orange. Or whatever color it is. Let's see. Okay, so start on this alkene carbon. I'll circle it and decide, is the hydrogen the next atom? Then the hydrogen or the carbon have a higher atomic number. Carbon's element number 6, so it wins over hydrogen. Go to the other alkene carbon. Here's carbon that's making a double bond. And we got a carbon up here versus a hydrogen. Oh, carbon wins again. And then our two highest priority groups, the winners, the box and the circle, are on opposite sides. That's not the same side. It's the other one, the E isomer. Entgegen? It's been a while. So you can either use trans or you can use E. Switch back. Okay, so let's kind of add them up like a math problem. All the prefixes go in front in alphabetical order. So B before H, 4 butyl, 5 heptyl. Oh, there's another prefix. Cis or trans? Sorry, trans or E? I'm gonna go with trans. You could also use E. Put in parentheses if you're gonna use it. And then I got this group, that group, I got that taken care of. Need the ene, need the parent. Oh yeah, the ene's already in there, the alcohol's already in there, but now you have to put in the numbers. So I'm gonna go oct, and then 6 begins the double bond, the ene group, and 2 is where the alcohol is located. And we have the IUPAC name. Woo. Cool. All right, enough of that, I think. Yes. Okay. If you see my videos from last semester, you know the drill. We present a new function group, we talk about how to name it, and then we discuss any interesting properties. Should have done that. Oh, we did. Alcohols are weak acids, weak bases. They can also hydrogen bond. I think that's all we need to know about the alcohol group. And after we discuss special properties, we talk about what reactions can make that new group, or what that new group can do, change into. So let's talk about how to make alcohols. And again, this is a review. Last semester, we discussed a whole bunch of double bond reactions, a bunch of alkene reactions. So if you like this explosion chart, we start with an alkene in the middle, and then you choose a reagent to transform it into something else, then awesome. This should be posted on Canvas. If it's not, send me an email and I'll find it for you. And just looking at this explosion of reactions, here's an alcohol. Okay, so one way to make an alcohol is take an alkene, double bond, add chlorine or bromine and water, and you make an alcohol as well as adding a chlorine. Yeah, 2 groups for 1. What else? There's some alcohols over here. So you can make an epoxide using this crazy molecule, abbreviated MCPBA. Oh yeah, you remember that. MCPBA, metachloroperoxybenzoic acid. Ooh, all right. Meta, we know what that means. The chlorine and this peroxybenzoic acid group. It's meta to each other. Cool. Take an alkene, add MCPBA to make the epoxide, and then open the epoxide with acid, dilute acid, make a pair of alcohols. Let's see, go around the ring here. Ooh, here's some alcohols down here. Okay, so this is the most common way of making alcohol. Is I think the 2 best ones are oxymercuration, demercuration, where you get Markovnikov products. So the hydrogen goes to the alkene carbon with more hydrogens, And the other group goes to the other carbon. And if you don't want that one, then do anti-Markovnikov addition using hydroboration oxidation. So these two are really important to know, remind yourself of. The cheap way of doing things is you can do Markovnikov addition with dilute acid. The problem is, watch, that's not how you spell a W. Watch for carbocation, CC plus carbocation rearrangements. Ew, it lowers your yields by creating more than one product, and it's more troublesome. You have to keep track of more than one thing on an exam. So I would avoid using these. Use oxymercuration, demercuration. You get the same molecules and a higher yield, more control. Any other alcohols on that list? Not from the alkene reactions, not that I remember. But again, more review. Last semester, we talked about SN2 and SN1 reactions. So if you have a primary halide, you can do a SN2 reaction on it with sodium hydroxide. Maybe add add a polar aprotic. Wow, I need a little review too. Aprotic. You need a polar aprotic solvent like DMSO or DMF, acetone, acetonitrile. One of those, not all four. With I know strong base, which might cause an E2 reaction, but adding the protic solvent will kind of help along. So we hope to get predominantly this alcohol. Hey, so that's how you make it with an SN2 reaction. Secondary halides work, but if you use a tertiary halide and base, ooh, you do get the E2 reaction, and that makes it alkene. No, we want alcohol. So then you have to switch mechanisms and use a weak base, water. Yep, and then you can make an alcohol if it's tertiary. Now, if you're thinking about synthesis, that's what this little graphic is trying to remind me, you get to start with alcohols. So with alcohol molecules that are 4 carbons or fewer containing an alcohol group, so you probably are not going to have to make these alcohols. You can actually start with this one. This has 4 carbons or fewer. We'll see shortly that when we make bigger molecules and do synthesis problems, we actually can create alcohols by some new reactions. So you're not going to use these two very often. Well, I would say the SN2 reaction you're still going to use from time to time, but there's actually some new and more clever and more useful ways of making alcohols. We'll see those soon. I think next week we got one more video. Dang it, I thought we were in the last video for unit 1, but nope, there's one more. Okay, switching gears and talk about, hey, what if you already have the alcohol group and you want to turn it into something else? Well, this is review also, right? So last semester, we talked about how you can treat it with strong acid, HCl, HBr, HI, and you can change well, if it's tertiary, it works really well. Sometimes if it's secondary, it works, but if it's primary, it's probably going to rearrange because you still need to know the mechanism of this. It's a carbocation mechanism. So yeah, I would also avoid this one too with HCl. Switch over to SOCl2. That works on primary and secondary and sometimes on tertiary. And then on exams, I'll just allow it to work on tertiary. PBr3, same deal. That's the preferred way of making a halide from an alcohol. And only use these if it's tertiary or you know there's not going to be a rearrangement, a carbocation rearrangement. And if you don't like any of those ways and you still want a halide, you can change the alcohol group to a tosylate. That was something else we discussed last semester. You can start with this reagent, tosyl chloride or p-toluene. Hey, now we know what toluene is, benzene with a methyl. Sulfonyl chloride. Sulfonyl talks about that sulfur with the oxygens. And what happens is you get substitution. This hydrogen and that chlorine form HCl, strong acid. So you must have pyridine here to act as a weak base to react with the HCl. It's called an acid scavenger. If you forget the pyridine during the reaction, you only mix these two, you get really low yields. What happens is the reaction gets started, you get the sulfur attaching to oxygen to make the product, p-toluene sulfonate ester, or the tosylate group, or you can just abbreviate it as OTS. And you start making some of that and you start producing HCl. And then before all the alcohol molecules react, they'll react with the HCl. Wait, what does HCl do to the alcohol molecule? Well, if it's tertiary, come on, HCl can react with the alcohols. And if it doesn't, if it's primary or secondary and it's not hot enough to form a carbocation, the H plus will still be attached to the oxygen and tie up a lone pair and put a positive charge on the oxygen, and that will prevent the sulfur from substituting. It'll stop the reaction. What can you do with this? Well, if you still want a halide, then add NABR, NaCl, and then you can do an SN2 reaction, as long as this is primary or secondary. And then everywhere you have your the tosylate group, that gets switched with your nucleophile. So that'd be another way to make an alkyl halide. But you could do other reactions too, right? So maybe you want to make an ether. So you have a strong base, good nucleophile. And now the oxygen can strike this carbon, as long as it's primary or secondary, and displace this leaving group, just like it was a halide. And now, whoops, let's draw it the other way. Then the nucleophile will attach to that carbon, and we'll have an ether. Cool. I'm assuming one of these is a hydrogen, because it has to be primary or secondary. Okay, those are all review. Hopefully that's not too bad. If I would say, if you had to remember one reaction, remember the PBr3. You've been using that for synthesis problems in the homework already. And when you see synthesis on the exam, PBr3 will transform the alcohols you get to use as starting materials into halides, and you can do reactions with those. All righty, let's move on to some new reactions. That's naming, new reactions. There we go. Okay, what else can you do with the alcohol group? Well, you can make alkenes out of them. So let's start, and then there's three ways. This is reaction number 1A. Works best with tertiary benzoic and allylic because you're going to make a carbocation. And tertiary benzoic and allylic carbocations are more stable than secondary and primary. So where's my example? Let's start with this molecule, a tertiary alcohol, and we add hydronium ion, strong acid. Oh, and we talked about this last semester. We had a hydronium as a reagent before. Sometimes over the arrow, you just see H+. Sometimes above and below the arrow, you see sulfuric acid, water, some other combination. It's all the same reagent. They all behave the same. It does, in this case, a dehydration reaction. We need to memorize the mechanism. Hey, it's going to be review. It's E1. How does it play out? Well, we have an alcohol, weak acid, weak base. We have a strong acid. Okay, let the strong acid work first. Strong acid, what are you going to do? Release or donate H+ to the other molecule. Specifically, lone pair on the alcohol group is going to grab an H+. You could put a 2 over here to say, hey, the new molecule has 2 hydrogens on the oxygen. But you can also swing those H's to the other side, and now it looks like water. I like that visual clue. Alcohol groups grab an H+ from strong acid, and they transform into a good leaving group, into the water molecule. Right now, the oxygen is making 3 bonds. That's why it's positively charged. Not happy about that. So it's just going to grab these electrons and run. This bond breaks. Sorry, carbon. Water just took off. Left you alone. And we have our tertiary carbocation. Watch out for those rearrangements. And again, that's why it's going to work best if you don't have a rearrangement, because if it's tertiary benzylic or allylic, these are resonance stabilized. Resonance stabilized carbocations, making them less likely to rearrange. On my exams, they don't. In the laboratory, nature, she makes the rules. They might rearrange a little bit, give you some side products. Okay, we're trying to make an alkene here, so the carbocation is not the final product. No, go to adjacent carbon. So find your carbocation, reactive center. Adjacent carbon, there's 3 to choose from, but they're all the same. They're all methyl. So maybe I'll draw a really big line to this hydrogen. So if you're looking at this video on your phone, you can see it. The water molecule we produced from that last step now serves as a base. Lone pair grabs a hydrogen off as H+. These bonding electrons collapse to make the new pi bond. And we have our alkene. Yay. And we also reform the hydronium ion. We start with that and we end with that. That makes it a catalyst. We're not going to use up any acid. That's a nice review of the E1 mechanism. What else do we need to know? Oh, the major product usually follows Zaitsev's rule. The most substituted alkene's a major product. What else is that? It's also the alkene with the most stuff hanging off of it. It's the major product. So let's do an example where you have to use Zaitsev's rule. So the question might read, draw the major product. That's not how I form it. I usually say predict products and circle the major product. Okay. Yeah, because I like seeing all the products and then you identify which ones nature prefers. So let's start with, what do I got? Ooh, I got that one. Okay, change it up a little bit. Different form of the same reagent, H+. Okay, so predict the products of this reaction, then circle the major products. Might be easier just go through the mechanism or just mentally do it in your head. The lone pair grabs H+ from water. Water leaves and takes these electrons, that bond, with it. So then you're going to make this carbocation, right? So the alcohol become water. It took that line away. So make sure you erase it. It's not there anymore. That bond's gone. Okay. This is tertiary. So we don't expect a rearrangement. Phew. Yay. So all you have to do is wherever the positive charge is, that begins your double bond. So we redraw the molecule and say, hey, sometimes double bond goes to the left. Sometimes it goes to the right. And sometimes it goes straight up that methyl group. Yep. So the carbocation was here, here, and there, and that's where double bond began. Okay, turns out there's not a 1/3, 1/3, 1/3, 33, 33, 33% yield of each molecule. Nope, nature has favorites. Zaitsev's rule helps you identify that major product. It's the most substituted alkene. Or I had students say the alkene with the most stuff hanging off of it. So if you circle the alkene, it's right here. This alkene has a methyl, half a ring, half a ring. it's tetrasubstituted. This alkene has a lot of stuff. It has a methyl, part of the ring, but it still has a hydrogen that has not been substituted. This is tri-substituted. This one's tetrasubstituted. Ooh, that's the winner. And this one, there's 2 hydrogens on this part of the alkene. It's di-substituted. This is our major product. And if you mark up your molecules like I did, make sure you identify, hey, I'm not circling this molecule. I know the directions say circle a major product. Just maybe identify, hey, this is the true major one, not that one. Yeah, nature makes a lot of this, some of this, and even less of that one. But you'll detect all 3 of those in the reaction mixture. Okay, another way, suppose you don't have a tertiary alcohol and you're worried about rearrangements. Time to switch mechanisms. You need to change your reagent so that you can produce an alkene that doesn't have a carbocation produced along the way in the mechanism. So a good reagent turns out to be phosphorus oxychloride mixed in with pyridine. Seeing that again. So let's start with, I don't know. Let me just look over here. I got that molecule, or cyclohexanol. Got a secondary one. This doesn't rearrange, but it is secondary. So if you tried to use acid on this, you'd have to heat it up and it might start to decompose because you're trying to make a secondary carbocation, not very stable, more difficult to make. Take some heat, might decompose the product, might decompose the reactants. So instead, you can use room temperature. At room temperature, you use phosphorus oxychloride, POCl3, and a little pyridine, which you can abbreviate PYR if you like. Or if you want to draw a benzene ring and put a nitrogen in there for one of the carbons, that's also pyridine. And then same pattern. Wherever the alcohol is, the OH group leaves and takes those bonding electrons with it. And then that carbon that used to have an alcohol begins your double bond. And it can go to the left. It can also go to the right, but hey, that's the same molecule drawn twice. You only have to draw the product one time. Cool. And the most important feature is no carbocation, so no rearrangement. Yay. Still follows Seitz's rule. It doesn't work that great for tertiary alcohols, but it still can work. So I would recommend, if you're going to make an alkene from an alcohol, use phosphorus oxychloride, or do the other reaction, which is actually a review. You can just do an E2 reaction on it. There's a couple ways of doing your E2 reaction. Let's say you have a primary alcohol. Ooh, you would totally lose points. You try to heat this up, an acid, and say, hey, Dennis, I want this molecule. And I would say, ooh, in the lab, you're not going to get that. So you need to do a different way because it's primary. It's going to be really hard to create a primary carbocation. So switch over and use the phosphorus oxychloride, POCl3 with pyridine, or just slide over to the previous slide and take a look at the tosylate group. Do this reaction first, changing the alcohol group into a good leaving group and getting it set up for, well, not an SN2 reaction, but an E2, because E1 and E2 reactions make alkenes. Whoops, I'm too low. Come on. Oh, it's over there. No, it's not. It's over here. Here we go. Okay. Let's just clean this up. Okay, so take that alcohol. It doesn't have to be primary, but definitely if it's primary, consider using this reaction or the POCl3 reaction. I forget how many alcohol carbons I had. Maybe I had that many. Change it in a tosylate. So you have to remember that it's two double bonded oxygen, so sulfur with a chlorine, and then toluene. Tosylate starts with a T, so that hopefully reminds you of toluene with the methyl group. And then, yep, you need the pyridine again, PYR, or draw the benzene ring with the nitrogen atom. And then if you're writing out all your steps, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You can draw the whole darn thing again, but you don't have to. You can also just draw out the abbreviation, OTS. And then we want an alkene. So let's do an E2 reaction on this. An E2 reagent. And you can use strong base and water, protic solvent, right? So you favored E2 and not SN2. Or you can use sodium amide. That was our favorite base last semester for doing E2 reactions. And what happens is, well, we have to know the mechanism of the E2 mechanism. So let's review that. So the carbons attached to the tosylate go to its adjacent carbon where there's a hydrogen, and a strong base will remove that H. These electrons form the pi bond, and that kicks out the leaving group. 7 carbons, double bond right here. And you don't have to draw it, but you get the tosylate group, O minus, sulfur, O. And then the sodium is a spectator ion. It's going to pair up with the negative oxygen. But the NH2 molecule acquired another hydrogen. Now it's just ammonia. That's neutral. No reason for sodium to hang out there. I'm putting them in parentheses because you don't have to draw those on exams. Just trying to make the alkene. If you don't like tosylate, I don't blame you. It's a lot of atoms. Go PBr3. Or if you don't like bromine, no worries. Use thionyl chloride, SOCl2. Change the alcohol into your favorite halide. 7 carbons, and then put a bromine. And then do your E2 reaction. You could use sodium amide, or you could use the sodium hydroxide and water, or you could use any other base you want. Remember this pairing? Tert butoxide ion with tert butanol. Protic solvent again. Strong base up here. Potassium's positive, helping you identify the oxygen as a negative. It's a bulky base. That's really going to favor E2 then. It's not going to want to do SN2. It's too bulky. And so 7 carbons, double bond, beginning where the halide used to be. There you go. Cool. So now we know all about how to make alkenes out of alcohols. It's time for something else then. I think it's the last topic. 2 reactions. We can oxidize them. Let's move this out of the way. Okay, a little history here. That was a great movie by Julia Roberts called Erin Brockovich. It was a story about how she wasn't even a lawyer at the time. She was a paralegal assistant, but she took on the responsibilities of a lawyer and took down PG&E for this little town, Hinkle, where PG&E were doing some bad stuff having to do with cleaning reagents of their water towers or something, using chromium oxidizing agents. And the chromium was getting into the groundwater and contaminating the drinking water of the town. And a lot of the inhabitants were getting all these crazy rare cancers. And she traced it back to, and proved it was traced back to these chromium compounds that PG&E were using. So we're trying to phase those out, right? They're toxic and they're harmful to the environment. So that's a little bit of history you need to know. If you Google oxidation of alcohols, you're going to get tons of hits for this old reagent called PCC. It's called pyridinium chlorochromate. Let me see if I got it written out here so I can. Pyridinium chlorochromate. And it's got a high has chromium with a high oxidation number, and it's quite toxic. So we're going to avoid using that. If you want the structure, well, it's got pyridinium in it, so it sounds like it has pyridine in it, and you'd be right. So there's pyridine. It's going to be an ion. So like the ammonia becomes ammonium ion, NH3 becomes NH4 plus, ammonia becomes ammonium, pyridine becomes pyridinium. We're also taking on that fourth bond and positive charge. And then chlorochromate has this structure here. Anyways, too much about that old reagents. We're going to avoid using that. However, not every student had myself during first semester of organic chemistry. And if in your organic chemistry you were taught PCC and how to use it, I will permit you to continue to use that in the notes, theoretically, but not in lab, right? We're going to phase out the use of this reagent. Okay. The more modern, environmentally friendly reagent is this molecule called the Des-Martin periodinane, or you just can call it periodinane. It's kind of an insane periodinane. That's how I can remember it. Look at this crazy molecule. Look at all these oxygen atoms. So on the exam, if you want to use this reagent, sure, you could draw the structure you want, if you want, but you could also just write the word period followed by insane. No, I mean inane. And that's the reagent, periodinane. And then if I see that over the arrow, I say, yeah, I know what you're doing. It's mild oxidation. Where's the alcohols? Let's oxidize those. Again, there's lots of different ways of drawing the reagent. You can pick one of them if you so choose. First, before we start drawing products, let's get a little more information. Scroll down the key points. Here's the pattern. And I got a nice shortcut after I finished the second mechanism, the second reaction. There's no more mechanisms, not in this video. Mild oxidation. There we go. Okay. If you have a primary alcohol, the alcohol changes into an aldehyde. But if the alcohol is secondary, you get a ketone. If it's tertiary, it doesn't react. Oh man, I know. So start with the primary, secondary, tertiary. And those are just examples, right? You have to look at your full structure and see where the alcohols are. And then I'll take the shortcut, insane, and then period, and pyridinane. I'm going to treat it with this mild oxidizing agent, pyridinane. Okay, what happens? If it's primary, then you get an aldehyde. So you get a double bond between the carbon and the oxygen and lose the hydrogen on the oxygen. Technically, you also lose a hydrogen off of this carbon, right? Currently, there's 2 hydrogens. Afterwards, there's only 1. That's your aldehyde. If your alcohol is secondary, same pattern. Double up the bond to the O and lose that hydrogen. And again, there's a hydrogen here on this carbon that gets removed as well, oxidized. If it's tertiary, you get no reaction. You just get the tertiary alcohol back. Doesn't do anything. Okay, that's a crazy molecule. That certainly did not come first. PCC did, but before PCC, scientists knew about oxidizing alcohols. They just did it with overkill, too much strength. You can also do strong oxidation of alcohols. And the one I advocate is permanganate, environmentally friendly. Not in this form, this is a strong oxidizer, but it changes to less harmful forms of manganese. Cool. Trying to think if that's actually an essential mineral. I don't think so. Magnesium, Mg is. Anyways, KMNO4 works great. Sadly, though, these have not been entirely phased out. So they might appear on your exam. You still need to know these, even if you're not a chemistry major. Oh my goodness, if you are a chem major, yes, you need to know these. You're going to see these in future chemistry classes. But if you're not a chem major, you still need to be aware that they're still using these. So you might see them on the MCAT if you're going to take the medical college admission test or the dental admission test, the DAT. So you still need to know need to be able to recognize all 4 of these. But again, preference is potassium permanganate. Okay, this also oxidizes the alcohols. What happens? Well, if it's primary, you get carboxylic acid, not an aldehyde. That's the only difference. Turns out that all four of these molecules do produce an aldehyde initially, but they're strong oxidizers, and then they attack the product. The strong oxidizers change the aldehyde into a carboxylic acid. Same pattern as pyridinane. If you have a secondary alcohol, you still get a ketone. If you have a tertiary alcohol, it still doesn't react. Note to chem majors. Under rigorous conditions, I think it's with base. If you raise the pH and you heat it, you can get a reaction happen. We're not going to cover that one. Okay, so examples. Start with a primary alcohol. I'm going to use the same ones so we can just compare and contrast. Tertiary. And this time, choose any one of these four. They all do the same thing. Again, my preference is going to be KMNO4, but be ready for any of them. Okay, so you see a strong oxidizer. They're easier to spot because they have a whole bunch of O's, a bunch of oxygens, makes them strong oxidizers. It's kind of the pattern, right? 3 O's, 7 O's, 7 O's, 4 O's, lots of oxygens. Okay, check the degree of the alcohol. So go talk to the oxygen, but shy, so it's attached carbon. Hey, carbon, how many carbon atoms are you linked to? Just attached to one directly. Oh, you're primary. Dang it. Okay, is this an aldehyde or carboxylic acid? Well, it's a strong oxidizer. So you're going to get a carboxylic acid. Initially, if we had to do the mechanism, but you don't, you actually do get the aldehyde first, and then permanganate reacts with it again to change it into a carboxylic acid. Are some of you getting a little deja vu? We've seen that before last semester. What if you had an alkene and you treat it with permanganate? Well, more review. If we had ozone followed by zinc and acid, you just do your karate chop, get your two pieces, cut the alkene in half, and then stop the bleeding with some cotton balls, and you get a pair of aldehydes. That was mild oxidation of alkenes, but there's also strong oxidation. Same wording. You also chop, you make these aldehydes, but then permanganate attacks it again, and then you get a pair of carboxylic acids. Or if you have a double bond at the end of a chain, then you make a ketone and you get carbon dioxide. Okay, same deal here. The alcohol is primary. You don't chop the chain, just chop the oxygen off. No, you don't. Different pattern. You make double up the bond. Sorry, it's not exactly the same down here. That's too bad. But after you make the aldehyde, that was a common pattern. The aldehydes get attacked by permanganate, turn into carboxylic acids. Strong oxidizer with secondary alcohol, no difference. Just make the ketone. Strong oxidizer with tertiary, still no reaction. Nice. I think that's it, but here, just quick little review. Okay, so treat this for pyridinane, or we treat it with one of the strong oxidizers. I'll switch it up. Could be permanganate, doesn't have to be, it could be any one of those four. And then this could be any one of the five. You could add pyridinane or one of the strong oxidizers, so maybe one of the others. What is this? Sodium dichromate or potassium dichromate. Okay, I have to cheat. Yeah, that's the fourth one. I know, it's just switching the spectator ion. That's just dichromate twice. It's really the same reagent. I know, sodium versus potassium. It's a minor difference. Whoops. Okay, last idea here. This is a quick review. How do you protect the products? First, you have to recognize these as oxidizing agents. The pyridinane is a crazy molecule. It's got an iodide here and a carboxylic acid here. So it starts looking like benzoic acid, but instead of an H, you connect the oxygen to the iodine, kind of make a ring here. And then there's 3 acetate ions. Remember acetic acid? From Gen Chem, we just wrote it this way. They're all the same molecules. To the iodine, you connect 3 acetates. That's the insane pyridinane. Lots of O's. That's the pattern. Lots of oxygen, strong oxidizer. Okay, the pattern is take off the H, double up the bond. Strong oxidizer, take off the H, double up the bond. Oh, wait. Strong oxidizer versus mild, add another O. Oxidation usually results in more oxygens being added. Okay, strong or mild, pyridinane, whatever. Secondary alcohol, take away the H, double up the bond. Cool. Tertiary, take away the H, double up the bond. Wait, 5 bonds. Carbon can't do that. There's no reaction down here. Yay. Okay, so that's a nice pattern. Just be careful. Don't just walk away or do homework when you're really sleepy and leave that structure. Yikes, no, that doesn't exist. Okay, plenty for now. There's one more video to finish out Unit 1. We'll see that next week. See you next time.